Hello, everybody. This is Dr. Dadu presenting Latin squares design and now happy being. Introduction. This is a third in the series of lectures on design of experiment. Latin square design and R is the topic of the present discussion. For the sake of visualization, I couldn't help asking the researcher to also install ggplot2. Otherwise, you would have done, we did all there is to be done, but I wanted a visual display, a pictorial display to show the viewers the situation. That's why I said you should install ggplot2. If you do not have ggplot2, you won't be missing anything except that you won't have the pictorial representation. And I've kept it at the back, the last thing in the lecture. So if you couldn't install ggplot, no problem. Now, I've also assumed that you are fully aware about Latin square designs, the computation and everything, so that I don't have to bother about the theory as usual, is to go to the codes. Now, about the data, the experiment to obtain the data from was that of a population, small area on wheat plantation. I told you at the beginning of the series that the agronomists will find my lectures very, very interesting. It doesn't mean that these things could not be applied elsewhere, but most of the things, the examples that we'll be having are due to the ones you can get in an agricultural setting. Having it in the back of the mind that I work with the University of Agriculture. All right. So the population consists of a small area of wheat containing about 8 shoots, each shoot being slightly over 2 feet. There are 6 samplers, A, B, C, D, E, F, all experienced in studying the growth of wheat. Each sampler inspected each area and measured the height of 8 shoots, whose height were to give a representative sample of the shoot height in the area. The quantity that we'll be analyzing is the sampler's error. That is extremely important. Sampler's error, the errors made by the samplers, the mean. The samplers represent the experimental treatment in this case. There are 6 areas, each sampled by the samplers. This area will serve as the replication and they may be taken as the column of the 6 by 6 Latin square. The rows of the square prescribe the order in which each man sampled the 6 areas as contained in the table 4.7. That's the table, data table. All right. These are the samplers. There's a randomization process in form of the Latin square design. All right. So that's the data. And it's indeed a 6 by 6. All right. Manual computation will take you through all this. And you would arrive at this analysis of variance. Mind the analysis of variance, the uncalculated analysis of variance, because we are supposed to compare it with our computed analysis of variance. This is one of the ways through which we'll know that we are in line, like a structure walkthrough sort of a thing. Okay, initial codes and output. You're going to keep inside order. Replicates in this form. Then in areas, it will be kept in there like that. The samplers, the order in which the sample as contained in the data, then there are mistakes. And this is the rate at which they're making mistakes. That's the mean of their mistakes. Now, data itself, it's in form of data frame. Row will be factor on order. And column will be factor on areas. And then treatment factor These ones are samplers. Okay, the yield in this case would be mistakes. Then we fix the linear model. Mistakes on other areas, samplers, and the data being that the ANOVA will be this. Now it's time to compare. Compare what we have in here. See, 149 under the F value. It is 149. You see? And although obviously the computer will always be more accurate than the uncalculated, but that tells us the data was properly captured and our analysis are reliable. Comment. The analysis of variance is presented in the statistical, is presented with the statistical significance being noticed on areas and the samplers errors. And the errors made by the samplers are statistically significant. Even readings taken from some areas are prone to errors. That's what this is saying. Okay. Now the quotes to further burrow into the situation to know what is really happening. How come the quotes, how come the samples taken from areas are prone to errors, and what are the kind of errors associated with each sampler? Now, this code will enable us to know how they stand. But mind it, I've done something, although it's a linear model. We've been following my series of lectures, you will know how to fix a linear model now. But then, I have said samplers minus 1. This is technically so. If I didn't say that, it probably would have start from samplers B to F. It will not include samplers A. See, I didn't do that for order because it will only give you one shot. That's why, and you see, it's starting from order 2. I didn't do it for areas too. Why? It would only give you one shot, and that's one shot is being used for samplers because samplers is of extremely importance. It's more important than area than another. In fact, if you go back to this, you will see that order is not found. There's no statistical significance put on order. So I don't have to pay attention to that. I rather will pay attention to areas and then samplers. And you know samplers is of utmost importance. Okay. So they are all prone to errors. Our samplers are erroneous in their judgment. The least prone to error is sampler F. That's the least prone to error, but it too is erroneous. It too was found to be erroneous. Now, nothing wrong with the other, like the ANOVA said, but the areas, well, area 1, sorry, yes, areas here now, areas 3 and 4 are equally, samples taken from areas 3 and 4 are prone to errors, but they are not as severe as these cases with the samplers. See, but the least area, also area 5 is finally prone to error. Samples taken from area 5 prone to error, but area 6 is free. See, area 6 is just okay. All right. Now, having found that, we want a pictorial representation of what is happening. See, if you see pictorially, there are some things that the picture gives to you. But having to write the code for graphics, because pictorialization takes us to graphics, having to write the hard code for graphics is going to be extremely lengthy, and that will be far above the discussion here. That's why I said, okay, I can't help it. If I want to put visualization there, if I want to be a pictorial representation there, I will have to fall on the use on a written library, ggplot2. After installing ggplot2, which is most of the time compatible with all versions of R anyway. Almost all versions. I'll be interested in knowing a version of R that will not easily accept ggplot2. In fact, I think it ought to be in base R, but it's a library of its own. All right. If you install ggplot2, that's the only code you need to have a pictorial representation of what is happening. And the slide of the output is next. This is the slide of the output. See the mistakes. These are the box plots of each of the samplers. And like I said, F is the least prone to errors. Why do we say so? Yeah, although it has a big box, how come it's least prone to errors? You see, it's least prone to errors because his box includes the region 0. And what does region 0 mean? Region 0 says no error. So he can make no error, while others are very, very prone to errors. They are continually making errors. He can make no errors. So he's the least prone to errors. Okay, this is the furthest I intend to go with Latin square design. Watch out for the competition of another design next time. Please share, subscribe. Thanks for listening. Thank you and stay blessed. Thank you.